Okay, so let's build our first convolution simulation with including a matrix for the convolution. So let's start a new file. Simple illustration of convolution in 1D. And let's first build point spread function PSF. Maybe let's call it PSF. And start with something really simple. Let's have just have 7 ones. So this guy is the center, and there are 3 to the left and 3 to the right in this very simple convolution kernel. And oh yeah, let's save it. Lecture 2. So this is simple convolution. And let's construct our unknown signal f for our measurement model. So let's say f is zeros. Let's say it's a vertical vector of length 128, for example. So now it's only zeros, but let's start with something really simple and make half of f to be 1. Beginning to halfway, let's put it to 1. So that's something really simple. And then and maybe actually let's do it this way. Let's put the we may want to change the length of the signal at some point. Maybe we could even start with a shorter one. Okay, and then construct the convolution matrix. A would be convmtx, and I think it's this way, PSF, and then we give the size of the signal that the point spread function will blur or affect. I think it should work like this. And now simulate our measurement. So now what we would like to do is m equals a times f. Not yet with the epsilon. Let's do the epsilon a bit later. So this would be our first measurement model. Let's see what happens. Any guesses? Who thinks this will run without errors? No one. Yeah, you're right. There will be an error for sure, because the size of A is now wrong. And why is the size of A wrong? Let's see. So A should be square. We would like to work with putting in a vector of length n, and the output should also be a vector of length n. But now Matlab, again, because of the boundary problems, it gives us too many columns. So A actually looks like this. Maybe we could even try this first with a very short one. Let's take n to be just 8. And so we can better see how A looks like. Okay, so here is our A, and let's see what's going on. We see even on the first row, we see the full mask with 7 entries, which is not what we want, as we saw in how the matrix should be built up. The center point of the mask is this one, and it should be along the diagonal of the square measurement matrix. So these first 3 should not be there in our model. And then also the last one, again on the last row, this is the center of the convolution kernel. So that should be on the diagonal, so the matrix should end here. So the last 3 rows are too much. So we should modify the matrix, and we could be smart at this point and actually make sure that we can do it in a general way for any length point spread function. And in the interest of having a unique center point in the mask, let's now make the mask to have an odd length so that it has clearly a center point, and at both sides it has the same length guys. So let's put m to be 3, and now PSF would be 1s. For some reason I like to have it as a horizontal vector, I don't know why, but anyway. And how many? So we should have 2 times m plus 1. This makes sure PSF has a unique center. And then I think here we can now modify A, so we can have all the rows, but we remove some of the columns. So actually we go from m plus 1 until end minus m. I think. Let's see if this gives us a square matrix. Let's run. Now it runs. Much better. So, and size is 8 by 8, which is nice. And now we actually have what we want. We have the center point here, and 1, 2, 3 guys, and also here center point, and then the 3 guys. Yeah.
Now the mask is moving, like if we each step move 1 to the right, but would it be the same kind of problem if we said that, you know, for each step when it goes 1 time before it moves, say 2 or 3 steps, the row at once. So it's not like diagonally, but like on the for each row you move the mask like 2 or 3 steps forward.
Right.
What would happen?
That would be something else than the standard convolution. First of all, however, in the inverse problems context, it would really make sense, because then we could think that we have an idea of full measurement with the full convolution matrix, but then actually some rows are missing. So then, for some reason, we are not measuring all of the components of M in the full convolution, but maybe every third of them or something.
Have a bad measure.
Yeah, that would be a kind of missing data measurement. That would be one way to think about it.
Okay.
And that's something we will be looking at in the tomography case a lot, not having every tomographic direction view of the target. So then we have a missing data problem. But that's actually a very similar thing, the same thing in this context. Okay, so now we have such a case, and so now let's see, we have F. F is this one, and we can now do the naive inversion. We can see what would it be if we take, so, and now M is that one, and we can, and we get our F back perfectly. Nice. So our naive inversion works. So far it seems that there is no need for this course. I mean, it's really, we get a nice reconstruction. Let's see if we can get into some trouble by complicating things a bit. So first of all, let's take a longer signal. Maybe it will be a bit more realistic, and also we could take some. Let's make a picture in Matlab, and well, regardless of the software, when you're doing mathematical programming and modeling and simulation, it's really good to take a look at everything when you go on. That's just generally a good idea in my experience. So let's take a look. Let's plot f in black, for example. Keep it there, and then plot our measurement, let's say in red. Sorry. Let's see how this works. Okay. So we see our original f in black here, and our measurement is quite big. Well, f has maximum value 1, and the measurement actually has value 7. Why 7? We didn't normalize the mask. And of course it depends on the application. Maybe your measurement is such that it will give you 7s. It's completely okay. I mean, if your machine measurement device is like that. However, for our simulation purposes, it may be more convenient to keep the signal and its measurement kind of the same size. And for that, a good idea is to normalize the point spread function. So we can divide the PSF with its own sum. And let's try again. And actually, I think it's also good to keep the visualization as clear as possible. So let's have some parameters for controlling the plot appearance. So let's say fsize, let's try with 16, and line width, let's see how 2 would look, and have here and I think we could put for example, the X tick marks, we could put, let's say, 1 to n, and okay, and let's see. Something is better, something not so good. Maybe we could even okay, not perfect, but maybe not the best way to do it, but anyway. So now we see our signal and measurement not too different from each other apart from this jump location. And now we could also do the naive inversion. Let's call it f0, which would be this one, and we could actually have here maybe if I actually do it this way, if I put this one let's do that way, and now subplot, let's put 3 and here let's plot f and the reconstruction by blue, let's say, and see how the naive reconstruction works. We do have some problem. Our matrix is not invertible. However, let's try first if we can. Okay, so it's 64 by 64 matrix we can compute, and we can see that okay, we get a perfect reconstruction. So far so good. Also, we had a little problem if we increase the size of our problem to 128 by 128 matrix, then we see that our matrix is no more invertible. So there seems to be a bit trouble coming up, and I think it will continue if we have a longer signal. I think that trouble will persist. Yes, you see our matrix is not invertible. However, we can actually go around that just by using könökeppi, as my colleagues in Kuopio like to call it. This will actually, Matlab will automatically use least squares or some kind of, I think it's a least square solver for the equation. So then I think we should, no, we don't get away with that either, even in that case. So it seems there is some trouble with that, but if we keep with our 64, we are still in the perfect regime, all is looking nice. But now if we put in noise, if we have now a noisy reconstruction, noisy reconstruction, so noisy measurement. So let's have sigma, let's say 1% noise, and we have the noisy measurement equals AF plus epsilon, which for epsilon we put now sigma, the standard deviation, times rand n for normally distributed, sigma times rand n of size f m, I think. Maybe this is not possible. Let's do it. Rand n, it should be m, no, n1. And then let's do naive inversion. And see how that looks like. Yeah, so even with this perfect performance we see here, there seems to be some trouble when we have noise. And remember, I put in just 1% noise. Let's see how it looks like actually. So in this picture, I think we now have the perfect measurement M. But let's take a look at actually the noisy measurement there. So we can kind of see. So it's only 1% noise. So you see it's very little noise there, but here the noise is amplified quite a lot. Yes?
Yeah, it's the inversion matrix is that much higher with values.
Yes. That's exactly the problem, because here you see this guy is the one giving trouble. So even if epsilon is small, this error here can be big, like we see here. So there's a very small deviation here, but it gets amplified and multiplied in the process. This is the core of ill-posedness problems. This is something we need to overcome. So this is your first glimpse of the very core issue of the whole field. Noise is amplified uncontrollably when doing naive inversion. If we have more noise, if we have 10% noise, I think it will get worse. So again, you see a similar kind of amplification of noise.
Can we see the noise of 1 promille?
Sure.
Does it look okay?
So there seems to be kind of a linear amplification in this case of the size of noise. And we also saw that if we try to go to a bigger size problems, so our matrix is no more invertible, and we couldn't even use the Könökeppi operator. What we can do is we can use pseudo inverse, which is something we will learn or go through pretty soon in the course anyway. Pseudo inverse will work for non-square matrices as well. We will see why. But with this one, so now we can compute even with this larger, longer signals. So now it seems that we have no problems working with even longer signals. We can do it, but even this 1 promille noise that you suggested is blowing up. And it's blowing up worse and worse with longer signals, which is again something, it seems that this is something undesired. It's really a problem. Yes?
If we had normalized this, our
Points per
convolution,
yeah, PSF.
would it be like better result?
Well, a quick way to think about it is that the normalization is just dividing by a constant.
Yeah.
So the matrix is divided by a constant. So actually, whatever happens here is just multiplied by a constant. So I don't think it can have qualitative really any. Well, of course, we can easily try it because we can just leave this out and run. We see trouble. Trouble is a little bit smaller,
Yeah.
but trouble nevertheless. So the trouble gets now divided with some number, so it's smaller. But
Then make it big enough, then it's
Yeah, but
yes. So if we take a longer, we can take a longer point spread function, because then the number gets bigger where we divide. So
But isn't PSF like related to a measurement device?
it is, yeah.
So it's not arbitrary.
It's not. Yeah, it has to be. The measurement model device has to be modeled. Yes. And now,
You use positive 2 for like all the numbers. Is that just for like convenience?
yeah,
you
it's
can
just.
divide by 2, like
Yeah, we could.
almost every time, so it's nice.
Yeah, we could use whatever. I mean, I don't think that's really an issue. And now, yeah. And now you see, again we have the noise bothering us. Otto, actually, okay.
in some examples, the noise seems a bit periodical.
Yes.
Yeah.
Yes.
Why is that?
I think it's because of the singular vectors of the matrix A. That's something we will see when we look at the singular value decomposition, which actually we could do right now, because maybe it seems already curious, why is this instability happening, and is there something we could do about it? I wonder if this works. New. So what is happening here? Let me fix the notation. Okay, so how to think about this? How to think about this and how to know for a matrix if we can expect problems with this situation or not. The main mathematical tool we'll be using is the singular value decomposition. Actually, I think I will stop this.